Lesson 41, One-Way Analysis of Variance. Example 3. Scientists interested in the effects of aging on people have conducted several studies to investigate this issue. In one particular study, the reaction time in milliseconds for a sample of test subjects of various age groups were measured. The following table displays the results of this study arranged by the age of the test subject. So here are the resulting reaction times in millisecond by the age for 20 to 29-year-olds, 30 to 39-year-olds, 40 to 49-year-olds, and 50 to 59-year-olds. According to these results, can the scientists report that the mean reaction times are all the same for people in their 20s, 30s, 40s, and 50s? If not, what can the scientists conclude regarding any differences between the mean reaction times of people in their 20s, 30s, 40s, and 50s? So we'll address the first question first. Can the scientists report that the mean reaction times are all the same for people in their 20s, 30s, 40s, and 50s? Well, this question involves the population parameter mu, the mean reaction time. For people in their 20s, 30s, 40s, and 50s means that we're dealing with 4 separate population means, mu1, mu2, mu3, and mu4, where the first population refers to people in their 20s, the second population refers to people in their 30s, the third population refers to people in their 40s, and the fourth population refers to people in their 50s. Now here they want to know if the mean reaction time are all the same for the people in these age groups. That is, does the mu1 equal mu2 equals mu3 equals mu4? A one-way analysis of variance is used to determine if the means for more than 2 populations are all equal or not. In order to apply a one-way analysis of variance, each of the independent random samples must be selected from populations that reasonably follow a normal distribution with approximately equal variances. Thus, we'll be making these assumptions to conduct our one-way analysis of variance. Now, for the second question, if the conclusion reached in a one-way analysis of variance is that not all of the population means are equal, that is, we reject HO, which particular population means are not equal, and specifically how they differ, can be determined by constructing all pairwise comparison confidence intervals to estimate the actual differences in the population means with a 1 minus alpha times 100% simultaneous level of confidence. Now, 4 population means require 6 pairwise comparison confidence intervals. One to compare the mu1 to the mu2, and one for mu1 to mu3, mu1 compared to mu4, mu2 compared to mu3, mu2 compared to mu4, and mu3 compared to mu4. So we will begin this analysis of variance by conducting our hypothesis test procedure. The first step in the hypothesis test procedure is to state the hypotheses. And in a one-way analysis of variance, HO and H1 are always stated in the same manner. That is, HO is that all of the population means are equal, and H1 is not all of the population means are equal. After stating the hypotheses, HO and H1, we then identify our alpha level of significance. We will use the customary 0.05. Now we can use the TI-84 calculator to calculate the p-value to help us reach our decision. To do this, we need to enter the data into the lists. So we have 4 samples, so we need to enter this data into 4 lists. To do this, we press Stat and then Enter to enter the list editor. We need to clear the lists out of old data in order to make room for the new data. So we will clear out List 4, List 3, List 2, and List 1 by arrowing up to the list name and pressing Clear and Enter. Now, the first sample are the subjects in their 20s. The reaction times are 455 milliseconds, 420, 471, 442, 459, 397, 456. In list 2, we put the second sample, the reaction time of subjects in their 30s, starting with 477, 426, 406, 454, 448, 460, 463. List 3, we enter in the third sample, subjects in their 40 to 49 age groups, starting with the 468 millisecond reaction time, 430, 482, 461, 527, 472, 484. List 4 will contain our fourth sample, the reaction times of the subjects in their 50s, starting with 513, 556, 452, 487, 509, 478, and 526 milliseconds. Enter. Now that we have all 4 samples entered into our 4 lists, we can continue with the one-way analysis of variance hypothesis test by executing the ANOVA for the list 1, list 2, list 3, and list 4. To do this, we press Stat, arrow over to Tests, arrow up to ANOVA, press Enter, and then enter in the list. Second 1 for list 1, comma, second 2 for list 2, comma, second 3 for list 3, comma, second 4 for list 4. Close parenthesis, enter, and we have our result. The result that we require is the p-value. Rounding the p-value to 3 places after the decimal, we see that the p-value is 0.002. So now we can make our decision. Since the p-value of 0.002 is 0.05 or less, the decision is to reject HO. And when we reject HO, we have enough sample evidence to indicate that HO is not valid. And in a sense, we also have enough evidence to indicate that H1 is valid. So, based on this result, we can answer the question this way. Therefore, according to these results, the scientists cannot report that the mean reaction times are all the same for people in their 20s, 30s, 40s, and 50s. In order to determine which particular population means are not equal, and specifically how they differ, all pairwise comparison confidence intervals could be constructed using the 2SAMP TINT command on the TI-84 calculator to estimate the actual differences in the population means. For the 6 pairwise comparison confidence intervals to achieve the customary 95% level of confidence simultaneously, each individual confidence interval estimate must be constructed with a 1 minus alpha equal to the 6th root of 0.95 level of confidence. So, using the 2SAMP TINT command on the TI-84 calculator, we can estimate the differences in each of these 6 pairs of population means, starting with the mu1 minus mu2. To do this, we press Stat, arrow over to Tests, and then arrow down until the cursor is next to 2SAMP TINT. Then we press Enter. We have data as our input, And to compare the first population mean to the second population mean, we need to use the data in list 1 and list 2. Now, to have the 6 pairwise confidence interval estimates, to have 95% confidence simultaneously, we need to take the 6th root by pressing 6 and math and arrow down to the root symbol of 0.95. Pressing enter gets us the 6th root of 0.95. Pooled, it's always no, and then down arrow to calculate, enter. So here we see that the estimate is somewhere between negative 46.9 and positive 37.1. Now to compare the first population and the third population means. We press stat, arrow over to tests, select 2SAMP-TINT. Here we use the data in list 1 and list 3. Keeping everything else the same, we go down to calculate, and we find that the estimate ranges from a negative 78.4 to a positive 14.4. Now, to estimate the difference between the first and the fourth population mean, we press stat, arrow over to test, select 2SAMP-TINT. Here we use the data in list 1 and list 4 to make our interval estimate. Down arrow to calculate. We find that we get the value negative 111.6 to negative 8.7 as our estimate. Now, to compare the second and third population means, we do our 2SAMP-TINT command using the data in list 2 and list 3. Arrow down to calculate, press enter. We find that the difference between mu2 and mu3 ranges from negative 72.4 to positive 18.1. Now to do the estimate between the difference of mu2 and mu4, we conduct our 2SAMP-TINT command using the data in list 2 and list 4. Arrow down to calculate, press enter. We see that the estimate ranges from negative 105.9 to negative 4.7. Now for the last interval, comparing mu3 and mu4, we conduct our 2SAMP-TINT command using the data in list 3 and list 4. Arrow down to calculate, press enter. We get the estimate for mu3 minus mu4 to be somewhere between negative 81.6 and positive 25.3. Now that we've calculated all 6 pairwise comparison confidence intervals, we can look at the values of these intervals to reach an interpretation. Notice that when L is negative and U is positive, the interpretation is that there is no significant difference between the means. That's because the confidence intervals contain 0. And when the confidence interval contains 0, it implies that there is no difference between those two means. So in this case, there's no significant difference between mu1 and mu2, mu1 and mu3, mu2 and mu3, and mu3 and mu4. That is, in this case, there's no difference in the mean reaction time between peoples in their 20s and 30s, 20s and 40s, 30s and 40s, and 40s and 50s. Now these confidence interval estimates have both L and U as negative values. When both L and U are negative, the interpretation is that the first mean in the difference is less than the second mean. So in this case, the mu1 is less than mu4, and mu2 is less than mu4. In this case, the mean reaction time between people in their 20s and 50s and between people in their 30s and 50s are significantly different. They're different in that the mean reaction time for the individuals in their 20s and 30s is lower or quicker than the mean reaction time of people in their 50s. Thus, according to these results, the scientists can conclude that the mean reaction time for people in their 20s is anywhere from 8.7 milliseconds to 111.6 milliseconds faster than the mean reaction time for people in their 50s. Also, the mean reaction time for people in their 30s is anywhere from 4.7 milliseconds to 105.9 milliseconds faster than the mean reaction time for people in their 50s. Furthermore, According to these results, the scientists can conclude that there is no significant difference between the mean reaction times of people in their 20s, 30s, and 40s. Also, at this level of significance, there is no significant difference between the mean reaction times of people in their 40s and 50s.